Digital signatures. So far, we have not delved into any detail about digital signatures. In this section, we look at how digital signatures work and how they can be used to present proof of ownership of a private key without revealing that private key. The elliptic curve digital signature algorithm. The digital signature algorithm used in Ethereum is the elliptic curve digital signature algorithm, ECDSA. It's based on elliptic curve private-public key pairs as described in the elliptic curve section. A digital signature serves three purposes in Ethereum. First, the signature proves that the owner of the private key, who is by implication the owner of an Ethereum account, has authorized the spending of Ether or execution of a contract. Secondly, it guarantees non-repudiation. The proof of authorization is undeniable. Thirdly, the signature proves that the transaction data has not been and cannot be modified by anyone after the transaction has been signed. Wikipedia's definition of a digital signature. A digital signature is a mathematical scheme for presenting the authenticity of digital messages or documents. A valid digital signature gives a recipient reason to believe that the message was created by a known sender, that the sender cannot deny having sent the message, and that the message was not altered in transit. How digital signatures work. A digital signature is a mathematical scheme that consists of two parts. The first part is an algorithm for creating a signature from a message using a private key. The second part is an algorithm that allows anyone to verify the signature by only using the message and a public key. Creating a digital signature. In Ethereum's implementation of ECDSA, the message being signed is the transaction, or more accurately, the CACHEC 256 hash of the RLP encoded data from the transaction. The signing key is the EOA's private key. The result is the signature. Sig equals F sub sig of two things. F sub CACHEC 256 of M and K, where K is the signing private key, M is the RLP encoded transaction, F sub CACHEC 256 is the CACHEC 256 hash function, F sub sig is the signing algorithm, sig is the resulting signature. The function F sub sig produces a signature sig that is composed of two values, commonly referred to as R and S. Sig equals R, S. Verifying the signature. To verify the signature, one must have the signature R and S, the serialized transaction, and the public key that correspond to the private key used to create the signature. Essentially, verification of a signature means only the owner of the private key that generated this public key could have produced this signature on this transaction. The signature verification algorithm takes the message, the signer's public key, and the signature R and S, and returns true if the signature is valid for this message and public key. ECDSA math. As mentioned previously, signatures are created by a mathematical function F sub sig that produces a signature composed of two values R and S. In this section, we look at the function F sub sig in more detail. The signature algorithm first generates a temporary private key in a cryptographically secure way. The temporary key is used in the calculation of the R and S values to ensure that the sender's actual private key can't be calculated by attackers watching signed transactions on the Ethereum network. As we know from the public key section, the ephemeral private key is used to derive the corresponding ephemeral public key. So we have 1. A cryptographically secure random number Q, which is used as the ephemeral private key. 2. The corresponding ephemeral public key, big Q, generated from Q and the elliptic curve generator point, big G. The R value of the digital signature is then the x-coordinate of the ephemeral public key, big Q. From there, the algorithm calculates the S value of the signature, such that S equals Q inverse times the quantity, CACHEC 256 of M plus R times K, modulo P, where Q is the ephemeral private key, R is the x-coordinates of the ephemeral public key, K is the EOA owner's signing private key. M is the transaction data. P is the prime order of the elliptic curve. Verification is the inverse of the signature generation function, using the R and S values and the sender's public key to calculate a value big Q, which is a point on the elliptic curve. The steps are as follows. 1. Check all inputs are correctly formed. 2. Calculate W, which is defined as S inverse modulo P. 3. Calculate U1, which is defined as cacheq 256 of M times W modulo P. 4. Calculate U2, which is defined as R times W modulo P. 5. Finally, calculate the points on the elliptic curve big Q equals U1 times big G plus U2 times big K modulo P, where R and S are the signature values, K is the EOA owner's signing public key, M is the transaction data that was signed, big G is the elliptic curve generator point, P is the prime order of the elliptic curve. If the x-coordinates of the calculated point big Q is equal to R, then the verifier can conclude that the signature is valid. Note that in verifying the signature, the private key is neither known nor revealed. Tip: ECDSA is necessarily a fairly complicated piece of math. A full explanation is beyond the scope of this book. A number of great guides online take you through it step by step. Search for ECDSA Explained. Transaction signing in practice. To produce a valid transaction, the originator must digitally sign the message using the elliptic curve digital signature algorithm. When we say sign this transaction, we actually mean sign the cacheq 256 hash of the RLP serialized transaction data. The signature is applied to the hash of the transaction data, not the transaction itself. To sign a transaction in Ethereum, the originator must 1. Create a transaction data structure containing 9 fields: nonce, gas price, gas limit, 2, value, data, chain ID, 0, 0. 2. Produce an RLP encoded serialized message of the transaction data structure. 3. Compute the cacheq 256 hash of the serialized message. 4. Compute the ECDSA signature, signing the hash with the originating EOA's private key. 5. Append the ECDSA signature's computed V, R, and S values to the transactions. The special signature variable V indicates two things: the chain ID and the recovery identifier to help the ECDSA recover function check the signature. It is calculated as either one of 27 or 28, or as the chain ID doubled plus 35 or 36. For more information on the chain ID, see the raw transaction creation with EIP 155 section. The recovery identifier is used to indicate the parity of the Y components of the public key. See the signature prefix value V and the public key recovery section for more detail. Note: at block 2,675,000, Ethereum implemented the spurious Dragon hard fork, which, among other changes, introduced a new signing scheme that includes transaction replay protection, preventing transactions meant for one network being replayed on others. This new signing scheme is specified in EIP 155. This change affects the form of the transaction and its signature, so attention must be paid to the first of the 3 signature variables, V, which takes one of 2 forms and indicates the data fields included in the transaction message being hashed. Raw transaction creation and signing. In this section, we will create a raw transaction and sign it using the Ethereum JS-TX library, which can be installed with npm. This demonstrates the functions that would normally be used inside a wallet or an application that signs transactions on behalf of a user. The source code of this example is in the file rawtxdemo.js in the book's GitHub repository. Running the example code produces the following results. Note rawtxdemo.js. The output is rlp-encoded tx 0xe68 ... tx hash 0xAA7 ... signed raw transaction 0xF866 ... Raw transaction creation with EIP 155. The EIP 155 simple replay attack protection standard specifies a replay attack protected transaction encoding, which includes a chain identifier inside the transaction data prior to signing. This ensures that transactions created for one blockchain, for example, the Ethereum main network, are invalid on another blockchain, for example, Ethereum Classic or the Ropsten test network. Therefore, transactions broadcast on one network cannot be replayed on another, hence the name of the standard. EIP 155 adds 3 fields to the main 6 fields of the transaction data structure, namely the chain identifiers 0 and 0. These 3 fields are added to the transaction data before it is encoded and hashed. They therefore change the transaction's hash, to which the signature is later applied. By including the chain identifier in the data being signed, the transaction signature prevents any changes, as the signature is invalidated if the chain identifier is modified. Therefore, EIP 155 makes it impossible for a transaction to be replayed on another chain, because the signature's validity depends on the chain identifier. The chain identifier field takes a value according to the network the transaction is meant for, as outlined in the chain identifiers table. Ethereum mainnet 1. Morden or expense 2. Ropsten 3. Rinkeby 4. Rootstock mainnet 30. Rootstock testnet 31. Covin 42. Ethereum Classic mainnet 61. Ethereum Classic testnet 62. Geth private testnets 1337. The resulting transaction structure is RLP encoded, hashed, and signed. The signature algorithm is modified slightly to encode the chain identifier in the V prefix 2. For more details, see the EIP 155 specification.